Good morning, good afternoon, and good night, distinguished judges, respected professor, honorable guests, and fellow participants. It is a great honor and privilege for us to participate in the International Innovation and Entrepreneurship Challenge, or EIIC 2026, organized by the Ministry of Education Malaysia in Pahang on 2026. Allow me to introduce myself. My name is Teuku Imam Fradhean, and I am an undergraduate student from the Department of Electrical Engineering, Universitas Malikussaleh, Indonesia. Today, I am accompanied by the wonderful teammates. It is Fathi Annaqi, Riki Azril, and Azzuhra Nayla Evana Saragih. Together, we are proud to present our research entitled Stage of Charge Estimation Experiment on Machine Learning Based Hybrid Energy Harvesting System using ESP32. Okay, without further delay, let us begin our presentation. Okay, so in this slide, to understand why this research is important, let us first look at the global situation. According to international energy projection, renewable energy is expected to contribute nearly 60% of global final energy consumption by the year 2050. Indonesia has enormous renewable energy potential, including solar radiation, small-scale hydropower, and mechanical vibration that can be converted into electrical energy. However, these renewable resources are naturally intermittent because they depend heavily on weather conditions and environmental changes. One promising solution is energy harvesting, which captures small amounts of ambient energy and store it inside rechargeable lithium-ion battery. Among various battery technologies, the lithium-ion battery is widely used because it offers high energy density, long cycle life, and relatively low cost. Nevertheless, efficient battery utilization requires accurate monitoring of its charging condition. This is where state of charge estimation becomes critically important. Okay, on the next slide, it talks about core problem of this research. Okay, so unfortunately, conventional energy harvesting systems still suffer from several limitations. Most existing systems utilize only one renewable energy resource. As example, when sunlight decreases or environmental conditions change, power generation drops significantly. This causes unstable battery charging and reduced system reliability. Furthermore, traditional SOC estimation techniques such as column counting accumulate measurement error over time. In another case, like sensor noise, fluctuating current, and dynamic loading condition, further reduce estimation of accuracy. As a result, inaccurate battery information may lead to poor energy management, shorter battery lifespan, and unreliable operation of IoT devices. Therefore, a smarter and more adaptive estimation method is required. Okay, on the next slide, we'll talk about the urgency of our research. Rather than depending on only one renewable resource, we integrate multiple energy harvesting technology into a hybrid system. By combining several energy resources, the system can continue operating even when one source becomes unavailable. However, integrating multiple energy resources also increases system complexity. An intelligent energy management system is therefore essential. To make accurate charging and discharging decisions, the EMS requires precise real-time information about the battery's stage of charge. This is why machine learning becomes an attractive solution. Unlike traditional mathematical models, machine learning can learn nonlinear battery behavior and maintain high prediction accuracy under changing operation conditions. Okay, on the next slide, we'll talk about challenge that happen in our system of research. Okay, although machine learning offers excellent prediction capability, implementing it on embedded hardware introduces several technical challenges. The ESP32 microcontroller has limited processing power and memory compared to a personal computer. Therefore, the selected machine learning model must be computationally efficient while maintaining high prediction accuracy. Okay, so another challenge comes from noisy sensor signal caused by flashing loss and renewable energy variability. Finally, battery safety must always be maintained. Our energy management system must ensure that charging and discharging process remain within safe operating limits to prevent battery from degradation or failure. So from the sixth slide, we have a proposed solution from the challenge that we have talked on the previous slide before. So to overcome this challenge, our research proposes three main innovations. First, we compare three different machine learning regression algorithms like polynomial regression, random forest, and like GBM. Each algorithm is evaluated based on a predictional accuracy, computational efficiency, and sustainability for embedded deployment. Second, the best performing model is converted and deployed directly into the ESP32 microcontroller, enabling real-time edge computing without requiring cloud service. And finally, we integrate this intelligent estimator into a hybrid energy management system. And the machine learning model provides accurate SOC prediction, while a role-based controller continuously verifies operational safety before executing switching decision. This combination provides both intelligence and reliability. At the center of the system is the ESP32 dual-core microcontroller. It continuously collects multiple battery parameters, including voltage, current, power, and operating time. To simulate renewable energy resource inside a laboratory environment, we employ programmable DC power supplies together with a function generator. This instrument emulates energy inputs from the solar panels, picohydro system, and piezoelectric generators, and etc. All collected data are processed locally by the embedded machine learning algorithm running directly on the ESP32. This enables fast decision making with minimal latency and without internet connectivity. Okay, so here we are talking about the workflow of system. Okay, the process begins with continuous acquisition of battery sensor data. Voltage, current, power, and elapsed time are transmitted to the embedded machine learning model. The model instantly estimates the battery current state of charge. Okay, and this is estimate SOC is sent to the energy management system based on predefined safety rules and operating conditions. The EMS decides whether charging should continue, stop, or switch between available renewable energy resources. The switching network then executes the decision automatically. This entire process repeats continuously, allowing the system to operate autonomously with real-time battery monitoring and intelligent power management. So, in the final slide, we'll talk about the outcomes from our research. Okay, through this research, we expect to achieve several important outcomes, like first, highly accurate real-time state of charge estimation for lithium-ion battery, and then improve battery lifetime through intelligent charging and discharging strategies, and third, enhance energy efficiency by optimizing power utilization for multiple renewable sources, and fourth, like stable bus voltage and reliable power delivery under dynamic operating conditions. And ultimately, our research aims to establish a practical framework for self-powered off-grid IoT systems capable of operating independently using hybrid renewable energy harvesting. We believe this technology has significant potential for future like smart agriculture, environmental monitoring, disaster mitigation system, and maybe like remote sensing application. In conclusion, this research presents a practical and intelligent approach to improving battery management, paving the way for more reliable and sustainable hybrid renewable energy system. Thank you for your attention.